In the previous video, isosceles triangles, we talked a little bit about altitudes, medians, and angle bisectors, but this video will be solely dedicated to special segments of triangles, which include altitudes, medians, angle bisectors, perpendicular bisectors. So if you're still unsure about that stuff, last video, don't worry. This video will tie up all the loose ends. So the first thing we're going to talk about is the perpendicular bisector of a triangle. So before you read anything else, just focus on the two words that we're talking about. Perpendicular, which means to intersect at a 90-degree angle, and a bisector, which means to cut something in half. So all a perpendicular bisector is that it cuts one side of a triangle in half and is also perpendicular to that side of the triangle. So again, let's read the definition. A line that divides one side of a triangle into two congruent parts and is perpendicular to that side. So, pretty much what I just said. So if we look at this picture down on the bottom right, if we look at this conditional statement, if EC is perpendicular to AD, so let's draw that in right there, and AC is congruent to CD, so let's give them both congruent tick marks, then EC, this line right here, is called the what of AD? Well, that would be a prime example of a perpendicular, well, we'll abbreviate here because I'm kind of limited on space, bisector. Alright, so that's an example of a perpendicular bisector. So next, let's look at what's special about a perpendicular bisector. And it's right up here. If there is a point on the perpendicular bisector, then it is equidistant to the endpoints of that segment. So that sort of makes sense. So let's look at this picture down here. If M is on the perpendicular bisector of JL, so here's JL, and so this line right here would be the perpendicular bisector, because that's what it says right here. So we know two things. We know that this segment from J, and we'll call this point X, so JX is congruent to XL, and also that JL is perpendicular to the line XM. Those are two things we can conclude because M is a perpendicular bisector. And just sort of think about, if you look at point X, that's equidistant to J and L. And as we move up the perpendicular bisector, since it's moving farther and farther away, but going straight up from the side JL, it's still going to be equidistant from points J and L. So any point on the perpendicular bisector XM is going to be equidistant from J and L. So let's fill that in. If M is on the perpendicular bisector of JL, then M is equidistant from J and L. So again, any point on the perpendicular bisector is going to be equidistant from the endpoints of the segment that it bisects. And it makes sense because you start off in the middle of that segment and you go straight up. And as you move straight up without leaning to one side, since you're not perpendicular, it's always going to be equidistant from J and L. Now, let's move on to the next special segment, and that are angle bisectors. So that's a segment that lies on, a segment that lies on the angle bisector and has one endpoint at the vertex and another endpoint on the opposite side of the triangle would be called an angle bisector. So again, just a quick example. Here's a triangle. Alright, I'm just going to freehand bisect this angle. So these two angles are equal. Then this line, we'll call it AB, would be an angle bisector because it starts at the vertex and hits the opposite side, and it bisects one of those angles. So, if there's a point on the angle bisector, then it's equidistant from the sides of the angle. And again, that makes a lot of sense because if we look at GH as a bisector of angle EGF, this bisector is cutting the angle in half, so it's going right through the middle of the angle. So it's always going to be the same distance from sides EG and EF as you move farther and farther away from G, because by definition it's an angle bisector, so it's always going to be equidistant from those two sides. So let's complete the statement. If H is on the bisector of angle EGF, then H is equidistant from sides EG and sides GF. And one thing that I want to focus on, and I'm actually going to zoom in on purpose for a change, oops, I did not want to do that, is that when you want to measure if a point is equidistant from two sides, you have to make sure that you draw a line from that point that's perpendicular to that side. Because when you measure something, like say height, you always want to keep the ruler perpendicular to the ground, or else that wouldn't be a true distance. So another thing you want to keep in mind is that when you are seeing how far away that point is from the sides, you want to draw a line perpendicular to the side, and it hits that endpoint. The altitude of a triangle is exactly what it sounds like, because if you associate altitude with height, then let's go back. If you associate altitude with height, then you could think of the altitude as the height of a triangle. So, by definition, it's a perpendicular segment from the vertex to the base, or line containing the base. So, if you look at the picture below, FB is perpendicular to AD. So let's mark that off. And I'm going to change the color too. And then FB is called an altitude because it's starting at the very tippy top of the triangle and it's coming straight down perpendicular to the base. And again, you can have an obtuse triangle like this, and if you wanted to measure the height of this obtuse triangle, you would draw the altitude straight down so that it was perpendicular to the base. So the altitude does not always have to be inside the triangle. The next special segment we'll talk about is the median of a triangle. And that's a line segment that connects the vertex of a triangle to the midpoint of the opposite side. So I'm going to draw 6 medians right here on 2 different triangles, so you get the hang of it. So it starts at the vertex and it goes to the midpoint of the opposite side. So that would be one example of a median. Or R to L would be another example of a median. Or Q to M would be another example of a median. Those are all 3 examples because it starts at the vertex and hits the midpoint of the opposite side. In the other triangle, we could draw MP, that would be a median, LQ, and NO. So it connects a vertex to the midpoint of the opposite side, which is different but similar to the mid-segment of a triangle. So that could be confusing, but you just want to be able to organize in your head that a median connects a vertex and a midpoint. A mid-segment connects 2 midpoints. So, in the triangle on the left, connecting L and M, like so, would be one example of a median. L and N would be another example, and NM would be another example, because those are all segments that connect 2 midpoints. In this triangle, we can connect OP, so that would be a mid-segment, OQ would be a mid-segment, and PQ would be a mid-segment. And there's 2 special things about a mid-segment, and that is that the mid-segment is half the length of its base, and also that the base of a mid-segment, the base and the mid-segment are parallel. So again, just a little quick example. Oops, sorry for getting dizzy. I'm still learning this. If we draw a little triangle right here, and let's say we knew that this base was 10, well, if we found the 2 midpoints on the opposite side and connected them, we could figure out that this new segment, this mid-segment, would be 5, because it's a mid-segment, because it's connecting the 2 midpoints, so it has to be half the base. And it sort of makes sense, because you're going halfway up the side of the triangle in each case, and then you're drawing a line connecting those 2 midpoints, so it makes sense that 5 is half of 10. Another thing is that this mid-segment and the base are parallel. So let's just say they told you that this angle right here was 40 degrees. Then you can also assume that this angle right here would be 40 degrees as well. Alright, so let's try one more problem. And let's just mark off everything that we could know about this picture. So if we look at this base along the bottom, it's going to be, segment AC is going to be 12. So since we know that G and H are midpoints because G cuts AB in half and H cuts BC in half, we know that GH is a midsegment. So it would have to be half the base, which is 12. So GH would have to be 6. And you can make similar arguments for side AB and the midsegment HI and figure out that since AB is 8, HI is 4. And likewise, since the base, or this side BC, is 14, then the midsegment parallel to side BC is GI. That would have to be half of 14. It would have to be 7. And what can we conclude about the angles? Well, I'll draw this in orange. Since we know that a midsegment and its base are parallel, then angle A and angle BGH would be corresponding angles, so they would be congruent. Same thing with angle C and angle BHG. They would be congruent as well because they are also corresponding angles. If you don't see it, just focus in on what I'm about to draw in yellow. Alright, we would have two parallel lines, like so, and BC would be the transversal, and hopefully you can see that these two angles are clearly corresponding. And you can make other arguments to figure out that these two angles, in orange, would also be congruent because they're corresponding angles. And essentially, you could figure out that other angles are congruent, but I won't waste your time. Alright, that was the end of the video. Thank you for watching. I hope it was informative, and have a good one.